Now we're going to look on some cool stuff we can do with Schnorr that helps us a lot. Multi-signature. Now we'll start with naive multi-signatures to show that it's easy in Schnorr, and then we'll show why it's problematic, and we'll actually show how we can use MuSig to solve these problems, which is a paper by Peter Willey, Andrew Postra, and others. Okay, so a naive multisig. Again, we have the glossary here for everyone to be reminded of the variables. So let's say we have two public keys, okay, P1 and P2. Each have their own private key, D1 and D2. Now, if they just, each one of them create a signature, a regular Schnorr signature. So we have S1, which has K1, the first nonce, plus E times D1, the first private key. And we have S2, which has K2, a different nonce, plus E times D2, the second private key. Now, if we just add those signatures together, S1 plus S2, what we get is, we get K1 plus K2, right? Plus E times D1 plus D2. Now, if we call K1 plus K2 K prime, and we call D1 plus D2 D prime, then we get S prime equal K prime plus E times D prime. Now, as you remember, this is how Schnorr signatures look. So what does this mean? It means that we got a valid signature for P prime, which is this private key, which is just the addition of both participants' private keys. So we got a valid signature for a public key, which is the addition of both the participants' public keys, which is pretty cool. And there is a bunch of problems with this. The first and most important one is called key cancellation attack or rogue key attack. What does it mean? Let's say we want to create a multi-signature using the scheme I just described, okay? So P1, the first participant, send the second participant his public key, okay, P1. Now, let's say I'm the second participant. What I can do is I can take my public key, subtract for it the other participant's public key, and then lie to him that my public key is actually P2 prime, okay? And then when he tries to add his public key with my supposedly public key, he'll get P1, his public key, plus P2 prime, which is the public key that I said I have, which is actually P2 minus P1. Now you can easily see that P1 and minus P1 cancel out, and the resulting public key is actually my public key, so that I can alone sign for that key, which is a problem. So how can we solve this? We can use MuSig. Now, the way MuSig solves this problem is called MuSig coefficients. The point of this is that we need to change all of the keys with some scalar which is unpredictable, meaning we needed to rely on all the public keys, so you cannot pre-compute that scalar, and it needs to be unique per key, so you cannot solve for it. So in this situation, we have two keys, P1 and P2, okay, again. Now we will create the coefficient. What we will do is we will hash P1, P2, and the public key that we're actually applying it to. So for P1, we will hash here P1, and for P2, we will hash here P2. We could also just hash the index or something like that, but for this exercise, we will just hash the full public key here. And then we take this coefficient, and each party multiplies his private key by that coefficient. Okay, and they get D1 prime and D2 prime. Now, to create the combined public key, what they need to do is they can take each other's public key, multiply by the corresponding coefficient, and add them up. Now, because this coefficient is based only on public keys, they're all public. Everyone knows everyone's coefficient, and that way they can all locally compute the resulting public key. But as you can see, because no one can pre-predict C1, meaning if you want to lie and say my P2 is actually P2 minus P1, you have a problem, because the public key you need to say you have is a result of the multiplication by the coefficient. Now, this coefficient is based on that result, meaning on after you subtract it. So you cannot do this. You cannot do this equation because you need to compute the coefficient to know the public key, but you cannot know the public key without computing the coefficient. So you cannot do the key cancellation attack because this is relying on the resulting public key. Okay, that way, this is non-interactive, right? because everyone can, as long as everyone knows everyone's public key, they can compute the coefficients, do it all locally, they don't need to interact. And that way they know there is no key cancellation attack because they apply the coefficient. Now that's for key generation, meaning we want to agree on what's our address. Now actually in signing there is another complication that we need to use something called a nonce commitment. Okay? Without this, not only there is no security proof, but there's actually been discovered an attack that exploits if you don't do this nonce commitment. So what is this nonce commitment? So after we have a key, we need to create a signature, right? This signature needs to have a nonce. And we also, as you can see in E, we hash that nonce. So everyone needs to get to a combined nonce. So let's say the two participants create their own nonces, K1 and K2. They multiply by the generator to get the public nonces R1 and R2. Now, what they could do is, as I've shown before, they could just add those R's together to get the combined public nonce and then hash it. But to make, as I've said, to make the security proof, and there is actually attacks, so to mitigate them, they need to first commit. What does it mean? It means that the first party creates K1 and R1, and then he sends the second party a hash of R1. Okay, so he commits to what the R1 he chose is. Now the second party does the same and send a commitment. Now that they all have commitments, they can actually expose the public nonces and combine them. That way no one can do something similar to the key cancellation attack by changing the public key, by changing the public nonce to be something related to other nonces, because they first need to commit to it. Now the reason we actually don't do this for the public key is because this is interactive, right? And they need to share hashes and stuff. And then after they share the commitments and they add up the nonces, they get R prime, which is the combined nonce. Now they can actually create E, which has the hash of R prime, what we just computed, P prime, which is the combined public key, and the message. And then they can use it to create the signatures.